Society in 1990 annual meeting, 10 U.S. and foreign patents. You listed in who's who of American inventors and society affiliations are American Nuclear Society, American Institute of Aeronautical and Astronautics, and also the Society of Automotive Engineers. I'd like to also point out that Dr. Brown has 2 patents. The nuclear battery is a patent that's also in your brochure, in your program. And the important thing to mention as well is that this patent is so valuable that Bell Labs Lucent Technologies decided to copy the patent. And they decided to make a replica that would fit into a digital watch for the last 25 years. You're about to hear about a real breakthrough technology that I'm very happy to introduce Dr. Paul Brown.
Thank you. Thank you. Of course, as Tom said, I'm here to talk about Betavoltaic batteries today. Specifically, I'm going to address the tritium battery. The tritium battery uses tritium as the isotope because it's relatively benign. The tritium battery is a thin film semiconductor device which produces about 30 microamps of current per square centimeter of area from a film only 4 microns thick. French rolled, these film foils may be packaged in any convenient form with an operating life of more than 10 years of constant duty. That's every hour of every day for 10 years under full load. The application of tritiated amorphous silicon as an intrinsic energy conversion semiconductor for betavoltaic devices is what I'm presenting here today. Analysis of the betavoltaic application shows an overall efficiency of 25% for tritiated amorphous silicon. A betavoltaic battery is a nuclear battery that converts energy from beta particles released by a beta-emitting radioactive source, such as tritium, into electrical power. Common semiconductor devices or designs of betavoltaic batteries use a semiconductor p-n junction device that is either directly exposed to beta decay or is illuminated by photons created when betas strike a phosphor. These common betavoltaic batteries suffer from technical problems in that the directly irradiated cells suffer material degradation of the p-n junction, limiting the operating life to days, while the photoconversion systems are indirect and limited by efficiency to less than 1%. A limitation of the aforementioned betavoltaic batteries is the self-absorption of beta energy in the radioactive source itself. In order to reduce the self-absorption of beta energy, the radioactive isotope must be incorporated into the lattice of the semiconductor. Tritiated amorphous silicon is a novel thin film material where tritium, a radioactive isotope of hydrogen, is bonded with silicon in the amorphous network. Tritium has a half-life of 12.5 years, is overall a benign radiation hazard, and the pure beta decay of tritium produces a beta particle with a mean energy of 5.7 keV. Thin film contact potential tritiated amorphous silicon cells have been built. These cells, called tritium batteries, have a specific power of 24 watts per kilogram, a full load operating life of 10 years, and an overall efficiency on the order of 25%. Cheap, long life, high energy density, low power batteries. I first disclosed this technology and the method of producing tritiated amorphous silicon January of 1990. Today this technology is patented with additional patents pending. It's been verified and several institutions are now developing manufacturing techniques. The betavoltaic effect may be defined in simple terms as the conversion of ionizing radiation to electrical energy by a material or a combination of materials. Radiation that is absorbed in the vicinity of any potential barrier, say a p-n junction, a metal semiconductor contact, or an electric field, will give rise to separated electron-hole pairs, which in turn flow as electricity due to the Volta effect. Of course, this occurs to a varying degree in different materials and geometries. So then beta decay generates ions in the semiconductor, and those ions migrate across the voltage barrier in much the same manner as in a solar cell, with the radiant energy of the sun replaced by the emitted beta flux. The emitted high-energy beta particles from the radioactive source traverse the cell material, losing energy and creating electron-hole pairs. Those carriers within the diffusion length of the junction are swept across, contributing a current. The highest device efficiencies are achieved by choosing a wide bandgap material capable of absorbing high-energy beta particles without degradation. Further, it should be noted that device efficiency increases with increasing source energy and beta flux. The number density of electron hole pairs generated per second in a tritiated amorphous silicon film is given here by equation 1. In a tritium battery, electron hole pairs are generated within the intrinsic layer and are separated by the electric field. This device is analogous to a photovoltaic cell, and the current voltage equation can be written as shown here by equation 2. The beta-induced current is related to the generation rate of electron hole pairs, the size of the device, and the efficiency of the electric field in separating the charges. The beta-induced current may be expressed by equation 3, while the open circuit voltage is expressed by equation 4. The entrapment of tritium is particularly apt in this application as it is readily substituted for the hydrogen present in hydrogenated amorphous silicon semiconductors with good intrinsic electronic properties. Radioisotopes other than tritium may be used as a source of energetic electrons, as well as other forms of energetic nuclear radiation, such as krypton-85, for example. The betas in a tritiated amorphous silicon film can also give rise to beta conductivity that is of a similar behavior to photoconductivity. This beta conductivity can be written as shown here by equation 5. A tritium battery consists essentially of a tritiated amorphous semiconductor sandwiched between two dissimilar metals, that is, metals with different work functions. The beta-induced electron hole pairs are separated by the electric field present, thus giving rise to an intrinsic nuclear battery, which is similar to a betavoltaic battery, but is powered by tritium decay betas rather than external electrons. Today we'll present a description of the properties and methods of preparation of amorphous semiconductor, concept and theory of tritiated amorphous semiconductor applications. All films were deposited using an ion sputtering system. Hydrogenation of amorphous silicon is essential as it serves to significantly reduce the defect nature of amorphous silicon by terminating a majority of the defective silicon bonds. Typically 10 to 25 atomic percent hydrogen is incorporated into amorphous silicon hydride to obtain a material with good semiconductor properties. The hydrogen is bonded to silicon and can be chemically stable to temperatures of 300 degrees C. Tritiated amorphous silicon can be deposited in the form of small and large area thin films onto a wide variety of substrates, electrically conducting or insulating, using low temperature processing techniques. Various ion sputtering plasma deposition techniques differ only by the form of excitation used and in the resulting range of operating pressure. All our thin film tritium batteries are produced here. The metals as well as the intrinsic layers were deposited using our ion sputter deposition system. This system consists of a substrate holder at one end with the there is a heating element directly behind that, and this is the target holder at the other end. The substrate holder can be heated to 300 degrees C and can be biased from floating to ground potential. Tritium was stored on a tritide on a depleted uranium bed and was released by heating the bed. The temperature of the bed was used to control the equilibrium partial pressure of tritium over the bed, and a micrometer valve was used to introduce the tritium into the chamber. The system was pumped with a turbomolecular pump backed by a vacuum pump. During the tritium depositions, the exhaust of the vacuum system went to a tritium scrubber, which traps the tritium as tritiated water. The entire deposition system is housed in a nitrogen glove box. The tritium content of discharged deposited amorphous silicon film can only be indirectly controlled via the discharge parameters and the substrate temperature. However, these parameters also affect other aspects of film growth. The relatively low pressure required to ignite a discharge allows co-evaporation of silicon to directly control the silicon-tritium ratio. In this design, silicon is evaporated by RF inductive heating of high purity silicon held in a fixture. This provides relatively uniform heating. Our tritium scrubber is a design modeled after the tritium scrubber in use at Lawrence Livermore. A tritium scrubber positioned after the two vacuum pumps is used to strip tritium from the chamber effluent by converting the tritium gas into tritiated water, which is collected in a desiccant. The scrubber consists of a stainless steel cracking chamber filled with catalyst, which is heated to a temperature of 1,000 degrees Fahrenheit to ensure combustion of hydrocarbons over the catalyst, including methane. The heat is provided by a tube furnace, which maintains constant temperature to within 2 degrees. From there, the effluent passes through a gas-to-gas condenser consisting of 20 turns of stainless steel tubing cooled by a fan. The cooled effluent and condensate then pass through 2 molecular sieves connected in series, each made of stainless steel and filled with desiccant. A centrifugal blower is attached to the outlet port of the molecular sieve to draw gases out and into the exhaust stack ventilation. A getter bed consisting of 800 grams of zirconium manganese iron, which is known as ST909 alloy, is positioned downstream of the centrifugal blower for the purpose of scavenging trace quantities of tritium before venting the chamber effluent. The scrubber system is configured so that the deposition process can be carried out in a once flow-through mode or with the process system isolated. Pardon me. Anyway, the latter is the preferred mode of operation where the chamber effluent gases are continually processed, yet the scrubber system volume is sufficiently large to ensure that the downstream pressure is below the required backing pressure for the turbomolecular pump. Here we have the short circuit and open circuit voltage curve for a typical tritium cell. The intrinsic tritiated amorphous silicon layer was formed by initiating a discharge and introducing tritium gas into the reaction chamber. The structure of the tritium battery was nickel foil substrate, intrinsic layer of tritiated amorphous silicon, and zinc. Fourier transform infrared measurements indicate that tritium atoms were bonded with silicon atoms. The bonded tritium concentrations were up to 25 atom percent. Tritium outgassing measurements were performed on the tritiated amorphous silicon films, and it was found that tritium was stably bonded in the film at room temperature up to 300 degrees C. Tritiated amorphous films are mechanically stable, free of flaking or blistering. They have good adherence to the substrate, and they may be simultaneously deposited onto both conducting and insulating substrates using a discharge in a tritium plasma. The silicon layer The silicon layer, sputtered in a tritium argon ambient at temperatures below 300 degrees C, results in a tritiated amorphous silicon film with the tritium concentration being variable from 5 to 30 atom percent, depending upon deposition conditions. Thank you. The optimum tritiated amorphous silicon thickness is a trade-off between capturing all the beta energy and collecting all the generated electron-hole pairs. Most of the beta energy is captured in a 2-micron thick film. Tritium batteries display a damage mechanism the same as the well-known Stabler-Wronski degradation seen in all amorphous silicon photovoltaic devices. Stabler-Wronski degradation is driven by electron-hole recombination and manifests itself as a decrease in the carrier diffusion length. For hydrogenated amorphous silicon photovoltaic devices, the highest initial efficiency occurs for device thicknesses around 800 nanometers. But because the degradation in diffusion length, the highest stable efficiency is obtained for 350 nanometer thick devices. From a stability viewpoint, the maximum allowable tritiated amorphous silicon film thickness falls in the 200 to 500 nanometer range. The maximum usable thickness of tritiated amorphous silicon film is limited by the degraded carrier diffusion length and is too thin to capture all of the beta energy. However, good device design allows most of the beta energy to be captured in the semiconductor. The basic concept is to use a multi-layer stack with the intermediate pairs being thin enough to be transparent. The outermost metal layers are thick enough to act as electron reflectors. These films are typically grown at a substrate temperature of 200 degrees C with 10 to 30 atom percent tritium incorporated into the film. The tritium concentration may be increased by reducing the deposition temperature, but at a cost of a reduction of carrier diffusion length. Cadmium sulfide is a wide bandgap semiconductor with a density more than double that of silicon. The higher density will result in more efficient energy capture from the high energy betas. In general, wide bandgap semiconductors have been found to be more radiation hard than low bandgap semiconductors. So cadmium sulfide is an excellent choice. Beta conductivity is a phenomenon evidenced by the increase in electrical conductivity of a material after the absorption of ionizing radiation. This effect is attributed to the increased number of free electrons generated by absorption of the ionizing radiation. Of course, recombination of the charge carriers does occur. However, during the time these carriers are free in the material, the conductivity can be greatly enhanced. For material in which one type of charge carrier predominates, for instance electrons, the change in conductivity with irradiation can be expressed as shown here by equation 1. Beta conductivity gain may then be defined as the number of inter-electrode transits that can be made by an electron in a conductor before the beta-generated hole is eliminated by recombination. For this case, where one type of carrier predominates, the gain is expressed as in equation 2. For an intrinsic tritium battery consisting of tritiated amorphous semiconductor material, the maximum beta power per unit area produced within the intrinsic region may be expressed as shown here. The maximum power may also be derived and expressed as shown. Of course, with these factors, we may then calculate the efficiency. The concept of intrinsic power conversion is achievable in tritiated amorphous silicon semiconductors for the purpose of low power applications. Tritiated amorphous silicon was used to make contact potential battery or a tritium battery with a specific power of 24 watts per kilogram and an efficiency of 25%. Specific power is a function of the power density and the half-life of the isotope used. Measurements indicate that tritium was stably bonded in the amorphous silicon network, and products based upon this technology are currently being developed. Now, at that point, up to now, I've just been talking about tritium batteries, tritiated contact potential cells. But there's a lot of interest in my oscillator battery also. So we'll talk about nuclear batteries in general. Devices for conversion of nuclear decay to electricity are nothing new, and many types exist. The simplest form of nuclear battery is the primary cell, as first demonstrated by Moseley in 1913 and extensively developed by Ernst Linder for RCA. A radioactive source rests upon a feed-through insulator, centrally located, within a conducting spherical shell. Beta particles emitted from the source result in a charge deficit or positive charge on the source, while the collecting electrode acquires a negative charge, establishing a difference in potential theoretically equal to the energy of the beta decay. Power is then delivered to the load in the usual manner. For instance, using radioactive phosphorus, which is a pure beta emitter with a 14-day half-life and a mean energy of 1 MeV, 1 gram occupies 1 cubic centimeter of volume and produces a primary current of about 2 milliamps. Assuming 100% efficiency, the total electrical energy or power emitted is 2 kilowatts. Here we have several patents for nuclear batteries which have been classed within the 4 major groups for their types of conversion systems. These technologies are possible due to the electrical nature of alpha and beta disintegrations themselves. Here we have one of Linder's many patents assigned to RCA for the primary cell, as we discussed earlier. The electric current produced by any source of charged particles may be expressed as shown here. We see that the current is determined by the rate of particle emission and the charge on each particle. This may be modified for radioactive substances to show the electric current as a function of the beta constant, or the decay constant, in the half-life of the isotope used. This relation may then be expressed in amps per gram for a predetermined quantity of radioactive substance. It follows that 1 curie of beta particles equals a primary current of 6 times 10 to the negative 9th amps. This is a p-n junction cell, as I discussed earlier, or I mentioned earlier. These batteries were used in long-life, low-power applications such as pacemakers before the development of the lithium battery. This is the most investigated form of Betavoltaic battery. Of course, here we have Rappaport's first patent, which was assigned to RCA for the p-n junction battery. This is my patent for the oscillator or resonant battery. This technology is still under development. Although I have greatly improved the design and new patents are pending, we will now consider the operating mechanisms. Here are several of the nuclear batteries I built and tested while with NuCell in Idaho, Oregon, and Canada back in the 80s. This is a schematic of the vacuum oscillator cell. We see the strontium beta source, a beryllium copper secondary emitter, a silver ribbon inductor, as well as the oscillation transformer. This entire assembly is then housed within a resonant cavity. Here we have a strontium-90 foil in the form of an annular cylinder. It's over on the right. In the center is just an aluminum drum, which the foil is to be mounted on. Now we've put the strontium-90 foil upon the mount. One of the end caps are in place. Now we have both end caps in place. This is just to hold the foil under the drum. And the strontium foil drum is then mounted on the end of a Kovar rod with a feed-through insulator. Here we have the components of the vacuum oscillator cell wired and ready for assembly. The beryllium copper foil is mounted on a Kovar rod. It's electrically insulated from the end plate. That upon assembly, this is about the strontium-90 foil to slow the primary betas and to emit secondary electrons. Next, the two-layer space-wound silver ribbon is put into place about the secondary emitter to collect the primary betas, as well as the secondary electrons, which are sprayed onto it. This is necessary to collect the charges in the high-voltage, high-frequency skin effect region of the conductor. Now the composite transformer is placed about the silver inductor, which is wired in series with a transformer primary. The transformer is an open-ended flux design with low damping, high Q properties. That is, it's an oscillation transformer. With a bit of vacuum grease and an O-ring, the central body is placed over the assembly. And now we have both end caps in place, and we're ready to put a vacuum on it. Here we have two versions of the oscillation cell on the test bench. This is the photo most of you have seen that was taken by the Idaho Statesman newspaper, and of course that was picked up by the Associated Press. Okay, now the way this actually works, to understand how the oscillation cell works, we must first look at the basic LC circuit. Theoretically, if an LC circuit were superconductive, an electrical impulse applied to it would oscillate between capacitive and inductive energy forever. However, in the real world, no such circuit exists, so energy is lost. By tuning the circuit into resonance, the only losses are the ohmic heating of the circuit itself. Consider a simple circuit with a voltage source, a load, and of course, a current is passing over the wire. The battery provides the electromotive force, and consequently, conduction electrons within the wire are set into a generally uniform motion. By definition, electricity is measured in terms of the number of charged particles, that is electrons, moving past a point in a unit of time, and we call this amps. Now we expose the wire to radioactive beta decay and observe what happens. The process by which a beta particle is absorbed is such that the beta particle collides with the molecular structure of the wire, knocking electrons free. This electron avalanche occurs until the beta particle has given up all of its kinetic energy and comes to rest. For a silver wire, a single strontium-90 beta particle will generate some 80,000 ion pairs within a distance of only 30 thousandths of an inch. An EMF is present across the wire so that these newly generated free electrons acquire a uniform motion, thereby adding to the number of moving charge carriers. That is measured in the real world as increased current. Okay. Here we have the simple circuit consisting of a battery, a load, and a section of wire exposed to beta decay. Bork received 2 patents relative to this simple means of current amplification. Now we apply the Bork effect to a simple LC circuit. Then through every cycle of the oscillation of which current is flowing, that current gets amplified by an amount proportional to the activity of the source and the applied voltage. All we need is an input of an amount of energy equal to the system losses to achieve a sustained oscillation. At this point we have a self-driven oscillator. Any energy contributed to this oscillating LC circuit greater than the losses must be removed through an impedance matching transformer, which yields high-frequency AC current to drive a load. Most of our experiments with these devices were operating between 40 and 400 kilohertz. This figure depicts the starting method employed, which involves the use of high voltage source to charge a capacitor of the tank circuit, which is then discharged to ground through a Class C amplifier at a rate equal to the resonant frequency of the tank circuit. A spectrum analyzer is used to monitor the activity within the tank circuit, and once a clean oscillation is started, the high voltage and Class C amp are removed. A moving particle has an amount of kinetic energy associated with it by virtue of its mass and velocity. If the mass and velocity are held constant, and we place a charge upon that same particle, then a magnetic field is generated by the moving charge that is carried along with it, all according to Maxwell's laws. Energy is stored in this magnetic field, and by integration we may show that this magnetic energy to be defined by E squared V squared over 3A. The charged ion in motion constitutes a current element of magnitude EU, and the magnetic field at any point from the sphere is given by the equation shown here. Now the presence of a magnetic field around the moving body implies that magnetic energy is stored up in the medium surrounding it. The energy stored up in a unit volume of a magnetic field is simply expressed here. By integrating the value of this expression over the region exterior to a sphere of radius A, the total magnetic energy due to the motion of the charged body is shown to be given by E squared V squared over 3A. Then the magnetic energy due to the motion is analogous to kinetic energy, for it depends upon the square of the velocity of the body. In consequence of the charge carried by the ion, additional kinetic energy is associated with it. If the velocity of the ion is altered, electric and magnetic forces are set up tending to stop the change of motion, and more work is done during the change than if the ion were uncharged. The ordinary kinetic energy of the body is 1/2 mv squared. In consequence of its charge, the kinetic energy associated with it is increased by the value E squared V squared over 3A. Oh, this is, I'll stop here. We'll stop here and take questions because we want to cut this short, right? That's good enough. I'll wind up here. So we have solid state batteries that produce pure DC output. They're about 25% efficient, and we're loading those up with tritium typically. The AC cells are still under development. They do produce higher power, but those are not production ready yet. Sure.
What applications do you see in the future for your batteries, and where are, if there are some happening right now, where are they?
Okay, the question was what applications do we see for these batteries? In the case of the tritium cells, small electronics where long life and accessibility are a problem, satellite power systems, remote repeater stations for some of the higher power stuff. For the low power stuff, using tritium, cell phones, portable electronics, portable computers, that kind of thing. We're currently talking to some large manufacturers with just that purpose.
What is the life expectancy of these batteries? How long
Well, the working life is 10 years. The output. Oh, the question was what's the working life of these batteries? The tritium cells output is determined by the half-life of the isotope used. In this case, it's tritium, which has a half-life of 12 and a half years. So that means, say, if it was a 1 watt battery, 12 and a half years from now, it'll still be developing 5 watts. So for a band of stable current generation, they have a 10-year operating life. They will continue developing power for the next 20 or 30 years, but of course that drops off with the half-life of the source.
conditioning electronics with the steady outputs then?
Okay, you wanted to know if you need conditioning electronics to have a stable output, and the answer is no. They are a constant current generator, roughly for about 10 years. Yes?
You're talking about putting these in consumer electronics. I mean, is there a disposal problem?
Well, there really isn't. Tritium is currently used in FAA mandates that tritium lighting is used on all commercial aircraft. All the exit lights and runway lights contain tritium. Tritium-containing products are currently in the market. As I said, tritium is relatively benign. In its gaseous form, it does present a potential health hazard in that it could be inhaled and converted to tritiated water in the body. But even if that was the case, it only has a 2-day biological half-life. It only resides in the body for 2 days, and there are there's no known dose of tritium that causes any biological effects, no level of harm. That's why tritium products are so easy to get into the market. Yes?
You said that your description of how the battery works, you said that beta particle hits the wire and then you get an avalanche. Did you say that electron production? Because my understanding would be that if a high energy particle hits the wire, you may see an avalanche of charge carrier production. But all that will do is give you a spike in your resistivity, in the local spot of low resistivity for a little while. When you heat up the wire, you get a high resistivity as a result.
Okay.
I don't see how that generates any kind of electromotive force within the resonance circuit as a whole.
Okay. The question was when a beta particle impacts a wire, he sees that ionization is produced, but he only sees that producing a localized increase in charge carrier density, so a reduction in the resistivity in that local area. And the answer is yes, absolutely right. That is absolutely correct. The only way those ions contribute any current is they have to be through what's called a diffusion link. There has to be a field and material combination such that I'm using a p-n junction as an analogy.
You have to treat it inside the junction?
Correct. Yes, it has to be done in the junction.
So what do those coils do?
Again, the question is, if, how do I want to phrase this question? Was,
In your prototype, do you have,
Okay.
do you have, in the central region, do you have p-n junction usually with tritium source? Or do you have,
No.
you just have tritium instead, and then you have it surrounded by coils?
well, actually, no. In those cells, we use strontium-90, and it's a vacuum cell. What we do is we,
Surrounded by coils.
well, it's surrounded by a silver ribbon, yes, a coil. So the beta particle from the strontium-90 passes through a beryllium copper secondary emitter that generates an avalanche of electrons. That avalanche of electrons is then sprayed onto the silver ribbon inductor, which is operating in a vacuum. That's how we collect the.
Do you have a vacuum diode?
Yes, well, to collect tens of thousands of ions generated by a single beta rather than one or two, which you would if you were just simply irradiating a wire.
That's different than the picture that was on the slide.
Well,
Interesting.
depends on which slides, but yeah, the lay explanation uses just a simple wire exposed in air, and it doesn't work quite that simply. Yes.
Hi, I'm an amateur experimenter. I've been working with dissimilar metals as plates, 6 inches apart. Got a little bit of voltage out of there, but 2 quick questions. I've been using aluminum and copper because they're cheap and readily available.
Sure.
I'm now aware of the term beta conductivity, and I think I need a source to find the right metal combinations. Is that available in, say, the Handbook of Chemistry or something?
The work functions of all the elements are tabulated in the Handbook of Chemistry and Physics, sure.
Including beta conductivity, which I think is...
Well, beta conductivity, if you want to buy my book, I address the issues, but there's no place where that's actually tabulated.
Okay.
But I give you the mechanics so that you can calculate it yourself.
Great. Second part of the question, real quick. Sounds like from his and your question, we would want to take the secondary of the transformer, which captures the beta particles. We would want to put some sort of beta source in the secondary of the transformer, or that might be an optimal design, right?
Absolutely.
Okay.
Yes. Yes, absolutely. The question was, have we explored any other means of starting the oscillation than using a Class C amplifier? The answer is yes, absolutely. The material I've shown here, this is really a decade old. This is all stuff I was doing in the 80s. The stuff we're doing now is patents are pending, and we are talking with some large companies, Mitsubishi, Nokia. Basically, I'm not at liberty to talk about what we're doing now, but the stuff we were doing back in the mid and late 80s is all public information. Yes?
If you were to lower the work function of the metals significantly, how would that improve the efficiency of the design? Have you considered amorphous diamond films as possibly one material probability or possibility?
Okay, there were 2 questions. If you lower the work function of the material, how does that affect the performance of the cell? And the second question was, have we considered
Amorphous diamond substrates or films to lower the work function?
and have we considered amorphous diamond substrates? The answer is you want as wide a band gap as possible. So ideally, what you want is a combination where you have a very high work function material, such as platinum, and a very low work function material, such as cesium. Problem is, in the real world, the cesium oxidizes and doesn't maintain that low work function. We've had very good results with a platinum. We use a platinum foil. Cadmium sulfide is the intrinsic semiconductor, and lanthanum hexafluoride as the low work function electrode. The diamond stuff, no, but I'm aware of some work going on in Canada where they're doing that. I believe in Vancouver.
So you need both high and low work function to get your large band gap?
You need a difference in potential, and the difference in potential is established by getting both a high and a low. If the two dissimilar metals are very close to the same work function, then your difference in potential is very low. Your efficiency is going to go away. It'll generate heat instead of electricity. Yes.
Well, just a point of clarification for the audience. I'm particularly fascinated by the fact that, on your 75-watt AC output strontium-90 cell, when you say that the kinetic energy of the betas is 30 milliwatts?
Correct.
Okay. Just to be sure that the folks get that point. I'd certainly like to see.
Well, I know where he's going with this.
Just to clarify the point.
The oscillation cell, the larger power devices. What he's pointing out is the strontium-90 source we use. That's a 1.1 Curie strontium-90 source. The textbook energy available from 1.1 Curies of strontium-90 is 30 milliwatts. That's 30 milliwatts of kinetic energy. The cell you saw developed 75 watts. Several orders of magnitude greater energy than theoretically available. And toward that end, that's why I was discussing the actual magnetic energy carried by these moving charges, because that's not accounted for with their kinetic energy. Now, that is my theory of operation. Just one moment. The accepted explanation. I'm not the first guy to notice that these nuclear batteries produce more electrical power than theoretically available. Corliss and others in the 50s and 60s, they called this the multiplication factor, and they simply applied it to or acknowledged that it existed and tried to explain it away by the ionization effect, the fact that a single beta particle will generate tens or hundreds of thousands of ion pairs. And the multiplication factor of these cells, they noted that for secondary cells, they saw multiplication factors on the order of 10 or 20 times, and some cells as much as 200 times. But in the p-n junction cells, they acknowledged that multiplication factors were on the order of 100 or 200,000 times. I've tried to go a step beyond that. I don't simply write it off as multiplication factor explains where this additional current comes from. I'm trying to go to the very root of the problem. And a moving charge generates a magnetic field. That magnetic field has energy associated with it, and by calculating the mean velocity of these charges, we can work backwards and figure the magnetic energy available, and it's in agreement within 5 or 6%. So I'm very confident that that's actually what's going on. You had another question?
Well, yeah, I mean, that's unusual. I certainly never heard the notion that we get higher magnetic charged particle than kinetic and a singly charged particle at high velocity.
Well,
Kinetic energy at that point.
the statement is that.
The question is, but you're telling the truth or not? I mean,
Okay, well, I'd like to answer that. The question is, he's never heard of magnetic energy being greater than kinetic, and I agree. It's not enough.
singly charged photon particle.
Well,
That's surprising.
let's use the analogy of a particle accelerator. If you take a slow-moving particle and you want to accelerate it to speeds close to that of light, you have to pump a lot of energy into this particle to accelerate it. And all charged particle accelerators do is pump in magnetic energy. In this case, we're talking about radioactive decay. This radioactive decay is already moving at near light speed. So it has this huge amount of energy that it's carrying along with it. What we're doing is essentially a particle decelerator rather than a particle accelerator.
They quote, what is the figure for the kinetic energy per beta? So when they quote that number, that includes any field energy that's in there. That's the difference between energy levels. That's,
Well, again, it's a game of numbers because I I use charged particle accelerator data to support my theory that that this, because you can work backwards from the observed mass of an accelerated charge. You can work backwards and account for the energy available.
I don't know what numbers you're using, but the energy that you're seeing, okay, has to be coming from the radioactive decay, right?
Absolutely.
So you're claiming a specific discrepancy between what you see and what numbers?
I must point out that this is not what I see. It's all textbook stuff. It's charged particle accelerators all over the world exhibit this same data.
Let's give another person a chance to
You're
question.
making a specific claim. I'm trying to get that.
We can talk about it more after I get out of here.
Last question. Strike short.
Yes, sure.
I didn't get the part where you said it caused an electronic, like you used the word avalanche. What was the step right before that? You said it creates an avalanche of electrons.
The absorption of any ionizing radiation causes an avalanche of ion pair generation. It's just the absorption of the kinetic energy of the particle. Yeah. Okay, well, thank you.
Very much, Carl.
Don't go rushing after the neutrons until you have first achieved star mode in air. Because once you achieve this mode, the only thing you need to do is to introduce deuterium gas and get your voltage up and supply enough current. It must be remembered that the past discussions are idealized situations. There are different moderate interpretations for what's going on, but this, for most purposes, is a simple layman's way to understand what's going on inside the fuser. It is nothing weird. There's no bizarre science going on. It's straightforward, normal science. But when you substitute deuterium gas or a deuterium-tritium mix, you're capable of doing fusion. Many of you may ask why star mode is so important and why superb ion recirculation is so important. The key thing to remember is that in the Poisson, the accelerated ions, especially at lower pressures, do not all collide. Instead, some zip right through the Poisson, exit the other side, and then once outside the Poisson, if they do not recombine, they literally turn around and then come back into the Poisson for a second pass, some a third pass, some a fourth. A lot depends on your critical pressure and the voltages used in the chamber. One mustn't think that you have perfect Newtonian orbits of these particles. That is not the case. But when you're in star mode, you're probably getting the best ion recirculation possible. It has been shown by George Miley and his group at the University of Illinois that the star mode is capable of producing at minimum twice the amount of neutrons as the common Poisson mode with no star. So this is what you want to shoot for.
Okay, the next video is a segment from NASA, and it will show the enormous reserves of helium-3 on the moon. This type of reactor will enable us to burn helium-3 efficiently.
has revealed much about our closest celestial neighbor and changed forever the way we view our own planet. Today, NASA is looking towards returning to the moon. A permanent lunar base would complement space station Freedom and provide a springboard for manned missions to Mars. And if researchers at NASA's Center for the Commercial Development of Space in Wisconsin are successful, the first lunar settlers will also be miners. Actually, this large automated vehicle will do most of the work, processing the moon's rocks and soil to remove a potentially valuable product, helium-3. Just 25 metric tons of this rare isotope, roughly the capacity of the shuttle cargo bay, could provide enough energy to generate all the electricity used in this country in an entire year. Helium-3 is produced by fusion reactions in the sun and carried through space by the solar wind. Earth's atmosphere shields us from the solar wind, but it has been depositing helium-3 on the moon for more than 1 billion years. Former Senator Jack Schmidt was part of the Apollo 17 mission, which marked our last, or as he likes to say, our most recent journey to the lunar surface.
We can't always use fossil fuels for the production of electricity. There are many environmental reasons why you don't want to do that. One of the most popular now, of course, is the addition of CO2 to the atmosphere. We don't need to panic, but we ought to be making those kinds of research and development plans that we have an alternative to coal and other fossil fuels in the not-too-distant future.
Studies indicate that the amount of radioactivity in a device like this generating energy from helium-3 will be 1 millionth less than in nuclear systems used today. And no greenhouse gases, acid rain, or solid wastes will result. The proposed mining system will be equally kind to the lunar environment. Once helium-3 has been boiled off, the untainted rocks and soil return to the surface, leaving it essentially unblemished. The process should also produce a number of byproducts, including water, which will be of great value to a lunar colony. And according to Jerry Kolsinski, a professor at the University of Wisconsin and member of the NASA Commercial Development Team, current oil prices makes helium-3 an even more attractive alternative.
At today's prices, helium-3 would be worth $4 billion a ton, which would make a shuttle load worth about $100 billion. And that's enough, I think, for any businessman to figure out a way to make a profit.
Helium-3 mining, using the moon's resources to meet future energy requirements on Earth.
Okay. Now this chart I have up here is a result of Daimler Chrysler duplicating my work. Last year at the Exotic Research Conference and at the Tesla Conference, I demonstrated the star mode effect. I freely put this information out on my website. An employee from Daimler Chrysler bought all the materials on my website, and now as a result, Daimler Chrysler is getting a patent pending on this, and they won't return any of my messages or anything. And you know, all I asked for is a little bit of credit for this. Actually, this isn't my main research. This is an offshoot of my research. Why I'm able to produce star mode in the center of those two electrodes is a result of the special coating that is on those electrodes, and that coating was an offshoot of our experiments with the moire stone material. You can see here I'm producing star mode in an air environment. If a vacuum is pulled on that chamber and then deuterium gas put in, we will get the results that Daimler Chrysler has reported in their laboratories. And mind you, I'm working out of a basement and, you know, very makeshift things, and I don't have research money coming from universities, or everything's coming out of my pocket. So, these guys got all the heavy equipment here, and this is the results of one of our offshoot products, well, not products, but offshoot research of a Mori device. Now we come to our second source of energy. The main component, okay, this is the star mode that Daimler Chrysler is showing up on their website. In the dock, you can, the video showing up on my demonstration at the one of the other conferences. This is exactly what's produced on the film. Farnsworth, in his fuser device, couldn't achieve the level of neutrons that he was seeking because there's a bugle effect, electron leakage. But with this method here, there is no electron leakage, and you can see the results. As a result, Daimler Chrysler has several military contracts relating to this technology. Granted, they spend millions of dollars to develop this, but give me a little bit of credit for what I've done here. Okay, now we come to our second source of energy. The main component that generates electrical power may at first glance appear to be nothing more than an atomic battery. It will be seen from the description that follows, its energy generating mechanism is entirely unique, and the advantages over prior atomic battery technology becomes apparent from the following description. I'll put up the next. I believe so. The Peralta radiant energy valve, I call it. There is a source of energy that could provide us with all of our energy needs for countless of generations. With this energy, we can reach for the stars, or at the very least, explore our own solar system. The fuel that I speak of is called polonium. It releases more energy than any single element ever to be discovered by man or woman. Polonium was the first element discovered by Madame Curie in 1898 while seeking the cause of radioactivity of pitchblende. Her electroscope showed it separating with bismuth. Polonium is also called radium F. Polonium is a very rare natural element. Uranium ores contain only about 100 micrograms of this element per ton. It is found in radium, and its abundance is only about 0.2%. In 1934, it was found that when natural bismuth, Bi-209, was bombarded by neutrons, bismuth-210, the parent of polonium, was created. Milligram amounts of polonium are now prepared this way. By using the high neutron fluxes of nuclear reactors, which you could use this setup here, this is a substitute for a neutron source, except for one thing. You can just shut off the switch and the neutron source is shut off. From this, you could develop an electronic nuclear reactor triggered by an instant source of neutrons, electronic neutron source. By using the high neutron fluxes of nuclear reactors, polonium-210 is a low-melting, fairly volatile metal, 50% of which is vaporized in air in 45 hours at 131 degrees Fahrenheit. It is an alpha emitter with a half-life of 138.39 days. A milligram emits as many alpha particles as 5 grams of radium. This represents a whopping 5 curies for 1/1000th of a gram, making polonium 5,000 times more powerful than even radium. The energy released by its decay is so large, 140 watts per gram, that a capsule containing about half a gram reaches a temperature above 932 degrees Fahrenheit. A few curies of polonium exhibits a blue glow caused by excitation of the surrounding gas. Almost all of its alpha radiation is stopped within the container that it is stored, where it gives up its energy. For these reasons, polonium is an attractive, lightweight source of energy. 25 isotopes of polonium are known, with atomic masses ranging from 194 to 218. Polonium-210 is the most readily available. Isotopes of mass 209, half-life of 103 years, can be prepared by alpha, proton, or deuteron bombardment of lead or bismuth in a cyclotron, but this method has proved to be quite expensive. Radioactive animations expelled from radium, thorium, or radioactive ores can be concentrated Could you show the glow regulator? Or was that the one before? Yeah. Can be concentrated on a negatively charged conductor. Radioactive matter decays and expels animations that will travel to a negative electrode. The collecting distance will depend on the potential of the charged wire. This animation is widely known as radon gas. It will decay to polonium in a few days. If thoron, radon-220, gas is generated, then the decay is almost instant. In a nutshell, polonium is deposited on a thin wire forming a cathode represented by number 2 in figure number 1 in the above drawing. It emits electrons, electricity. These electrons rush towards the cylinder anode number 1, thus generating electrical current. This is no ordinary atomic battery. We have a provisional patent that was granted a few months ago with my virtual lab associate in Australia. And we communicate through the internet and compare lab notes and do our work in our basements. The plated polonium heats the cathode wire too, dislodging millions more electrons than a cold cathode would in a conventional atomic cell. My unique design generates the high voltage normally associated with atomic batteries, along with increased amperage. A little extra amperage goes a long way in increasing the wattage to high levels. When positively charged helium atoms, alpha particles, collide with the electron cloud that envelopes another atom, its positive charge is canceled by collision. This is atomic absorption. Atoms ring like a bell when this absorption occurs. The ringing generates high energy X-rays, gamma radiation. The wavelength of this generated X-ray depends on the charge of the alpha particle and what type of atom it hits. If the X-ray generated has an energy level that exceeds 10 MeV, it is absorbed by atoms, in which case the neutrons are raised to excited energy levels. When they return to their ground state, they are broken loose from the shells of their parent element. Isotopes may be created by gaining or destroyed by losing neutrons as a direct result of this process. We can efficiently do this by exposing certain atoms to high energy alpha particles. This is what I'm calling alpha fission. From this model, it is clear that nuclear changes can occur by nuclear electronic stimulation. Go back to the decay charts. As you can see from these charts, that if thorium is used as a parent source, then there is minimal danger of radioactive contamination because of the very short half-life involved. The Perrault valve is a unique way to convert the energy of radioactive particles that are a result of radioactive decay to electrical energy. The energy of an alpha particle will be used as an example. The average alpha particle has a kinetic energy of about 6 MeV that will ionize inert gas in the valve. Therefore, if an alpha particle dissipates all of its ionizing energy in inert gas, about 100,000 electron pairs are generated over a path length of about 4 centimeters, 1.5 inches. As a result, a charge of 10 to the minus 14th coulombs can be collected by the electric charge inside the valve chamber. Could you show the Perrault valve? No, that's a glow regulator. Here it is. The Perrault radiant energy valve, shown here, has a cylindrical form. It has an axial, positively charged wire anode that extends the length of the cylinder. Negatively charged ions are attracted to the positively charged anode and arrive a few microseconds after an ionizing event, while positively charged ions are attracted to negative cathode cylinder liner few milliseconds later, these positive ions recombine with the negative ions. The result is an intense, short duration of electromagnetic energy. This energy now impinges upon the cylinder's photoemissive material, resulting in a flow of electrical current in one direction. This flow of current acts as a valve to many wavelengths of ionic energy. It prevents ions from returning to their originating source. This valve does not change high frequency to direct current. The valve prevents energy from flowing back from whence it came. Last but not least is my jewel, radiant energy. It will efficiently light lights, charge batteries. You can take that transparency off. Run motors and electrical appliances. This is the original Moray valve. It is a very old source of energy. It has been with us since the birth of our planet. It is clean, natural source of energy. It is my hypothesis that it is the very source that several inventors of yesteryear have tapped into without fully realizing it, with the exception of T.H. Moray. Around the year 1911, T.H. Moray was able to power a 16-candle power carbon arc lamp at about half of its light output. That's it. This is Moray's laboratory. You can see that he's lighting up a bank of lights here, running a heater, a motor, a small iron, all from a box about the size of a bread box. It's been said in some of the literature that this box produced about 50,000 kilowatts of power, but if you go over the calculations, that was not 50,000 watts available instantly. That was over a period of time. The calculations indicate that from a small bread box, it was producing about a continuous 4 kilowatts of power. Carbon arc lamp by about half its light output with a simple electrostatic charge obtained from an antenna and ground connection. So radiant energy power generation was born. In 1912, while Henry Moray was on mission with the Mormon Church in Uppsala, Sweden, he had a passion for crystal radio reception. Every spare moment he searched for a mineral that could possibly work as a radio detector. Moray had found 2 specimens that worked well as radio detectors. One was a sensitive galena that he found in a hillside, and the other was a white powdery stone-like material that he found in a railway car, located in Spisko, Sweden. From military records, we know for certain that the white material was fused silica. Back in the early days, quartz, silicon dioxide, was crushed and used for the mining roads. Moray could have taken the powdery quartz material, along with its impurities, and fused it with a welding torch, knowing that fused silica, silicon metal, in those days made a good detector for crystal radio. He also knew that galena taken from the hillside would make a good radio detector material. One day he put the 2 specimens back to back with a silver cat's whisker. And to his surprise, he got wonderful results. In fact, he found that he could drive a small horn speaker with the combination. The source of power was obtained from a local radio transmitting station. Later, Moray learned that he could also draw from the radio frequencies generated by nature. These towers back then put out enormous amounts of power. They were unregulated, and they could drift in frequency dramatically also. Sometime in late spring of 1925, Moray designed devices that could put out higher wattages. Oftentimes, people would demand that he draw too much power, and the white stone-like material would overheat and burn up. He was drawing too much current to the material, and it burned up. When he ran out of this material, he was forced to find a substitute. I have identified Moray's material from the hillside as being a type of Argentine zinc-ferrous galena. This he was able to synthetically duplicate. The formula is found in Moray's electrotherapeutic patent number 2460 707. Maury was never able to determine exactly what the impurities were in his fused silicon material. This forced him into exhaustive research with semiconductor materials. Silicon and ultra-pure germanium held the most promise. To increase the sensitivity of his semiconductors, he exposed them to radioactive emissions. As a result, he was able to formulate satisfactory mixtures. His greatest success was with a triboluminescent zinc mixture consistent of pure zinc sulfide that was doped with a bismuth activator. Today, these phosphors are known as electroluminescent phosphors, and to my knowledge, there's only one manufacturer in the country that produces this type of phosphor, GTE Sylvania in Towanda, Pennsylvania. The bismuth was first exposed to radiation emitted by a unique high-voltage powered vacuum tube that contained radium chloride. This created active bismuth, today known as polonium-210. He was doing this electronically by using the alpha particles within this tube. He was using nature with an electronic tube to produce an artificial fission. Today, this is done in a nuclear reactor. But you could design a nuclear reactor using this alpha fission process that's clean and that does not produce the deadly toxic materials that are byproducts of today's nuclear reactors. And I fear that the reason why they're still using these dirty reactors is because they want to breed these materials that are left over. And you know what they are. They produce bombs and weapons-grade plutonium that, absolutely foolish. We should stop making bombs and start powering the world. I've seen figures the other day, only 25% of the world is lit. The rest of the world, 75%, goes without power. And this is the reason why they have put out this radiation paranoia, so that we do not use this as a source of energy that could power our homes and our electric cars very cheaply. Right now in this country we have vast reserves of thorium, and you could see by the chart that the daughter products of thorium very short-lived. So if those containers were broken open, it would pose almost zero risk of radiation contamination. You don't want to breathe in radon gas or thoron gas, because when you take in radioactive materials into the body, they become very destructive. But if you do not ingest materials, then it does not harm you. The biggest scare tactic that they've used is the women that lick the brushes that they use to paint radium dials. And then also some of the quack medication that came out in those days, they put radium into tablets and people were consuming them. Of course, radium being very close chemically to calcium would deposit into the bone marrow and you die a very horrible death. And they use a scare tactic because if we use this clean source of energy, there is no more weapons-grade material available to them. And everybody has access to power their homes and electric cars for very cheap. Well, we're not done yet. Okay, this created active bismuth, today known as polonium-210. This is what Maury called artificial radiation. When added to zinc sulfide, it would glow a bluish green. When this glowing material was then doped into ultra-pure germanium, it made an excellent transistor-type material. Well, I'm showing I have 10 minutes, and I really want to get on to the part where we can actually tune into the RF frequencies that the Earth naturally generates and take this and produce usable power without... There's a possibility that's been brought to my attention that this could be done without using radioactive materials. Up until this time, I have been using I've been going to the mine in the back of my property with my son and extracting my own radioactive materials. It's legal as long as I do not transport the material off my property. However, we've reached a stone wall because if I take 1 millicurie of radiation off my property, they'll confiscate all my material, as they have done a gentleman, David Hahn, who was doing the same type of research, and throw me in prison. So this new doorway is really exciting for me, because that would mean that we could get a device out that, what can they say about it? There's no radiation in it. We'd be extracting the natural background radiation from the atmosphere and converting that into electrical energy. Okay, very, very quickly here, I'm out of time. I will be doing a conference in Arizona in July, Exotic Research Conference. I have 3 hours there, and I will be setting up radiant energy devices, and hopefully I'll be able to, in 3 months, and I'm very confident we'll be able to do this, bring in a device that's operating without radiation, at least 100 watts, and I'll be able to show the circuitry. Okay, let's go over this real quick because I want to get it in. Assume that the average reader of this treatise, I put this on the internet, will be familiar with the elementary principles of wireless apparatus. Granting this, it is, of course, reasonable to believe that such readers will understand how an oscillating current is set up in a circuit comprising an inductance coil of wire, capacitive condenser, and a spark gap. The condenser is charged with a high-tension current from any convenient source, such as a transformer or induction coil. And when the potential stored up in the condenser reaches a critical value, the air in the gap between the spark gap electrodes can no longer stand the strain, and the condenser discharges across the gap in a succession of crashing sparks. As the current from the condenser crosses the gap in one direction, it literally overreaches itself as a pendulum swings past the neutral point when given a push with the hand. When the first rush of current passes in one direction, a reversal of the cycle occurs and a second rush in the opposite direction is affected. This operation is repeated many thousands of times per second. The discharge gradually dies down until all the energy is either completely radiated or used up in heat or performing work. The oscillations cease once the potential across the condenser has been lowered to such an extent that the spark can no longer jump the air gap. The condenser immediately takes a fresh charge from the transformer, and the entire cycle of operations is repeated. It will be understood that all of this passes in a very small fraction of a second. The charge and discharge of the condenser taking place so rapidly that the observer can detect no change in the spark, which appears continuously to fill the gap. If the oscillating tank circuit has the correct impedance, reactance, and inductance, it will absorb energy from an external oscillating electrical source. Energy is captured. The tank oscillations can be kept alive by establishing resonance with the external source. Therefore, energy is not drawn from the transformer. In the case of the radiant energy generator, energy is harnessed from natural Earth radio frequencies generated by lightning strikes. What I have just revealed is the holy grail of energy. The implications of this discovery are far and wide. Is humankind ready for such a revelation? Thank you for your interest in my research. Maybe you have a time for a quick question.
Bruce, what's the voltage going through the RE valve?
I didn't realize that he put this up. Like I'm going to show my workshop, and I didn't have time here, only 45 minutes trying to condense all this great stuff. Oh, okay.
The voltage on the valve?
In this particular circuit, this is very basic to show. It's about 10,000 volts peak to peak, and about 25 kilohertz going through this tripler. what happens is the charge is built up. And mind you, when it goes through the radiant energy valve, this valve is a regulator to keep the voltage constant. And what we want here to pump this atmospheric energy is we want pure voltage with very minimal current. And what we discovered here recently, that if we put the best materials that we found so far to work is lead and iron. And what happens is when pure voltage and no current is passed over this arc, by what I believe to be the Barkhausen energy very intensely is exhibited. Then we take a tank circuit and absorb this Barkhausen energy. But if the slightest amount of too much current flows through here, this energy is not produced, it is not absorbed from the environment. What you don't see in here is an antenna and ground. And in the glow regulator, I've been using radioactive ores. At a negative potential, we coat the central electrode with polonium, which heats up that electrode. And the valve is constructed of two dissimilar materials thermoelectrically. When that polonium heats up the wire, electrons are expelled, and the greater energy is produced. That's where the energy is coming from. It's not coming from the power supply. But the notes that I've seen recently indicate that I do not need the radioactive material in here. There's another modification that is to be done that will take all this energy that's in our atmosphere, the RF energy, a lot of wavelengths, different frequencies. This energy is being produced when the lightning discharges, and there's about 100 lightning discharges per second someplace on the globe. This energy is like 2 million watts of energy released in each spike. This circuitry can tune into that. And until now, I've been using radioactive material, and I'm very excited when I get back to use this new configuration, because if it works, then we overcome the radioactive problem, and there will be no problem with it.
Bruce, if lightning strikes, how should I say, bring the voltage potential between the atmosphere and the ground back to a neutral state, each lightning strike, then that would mean an energy has reached equilibrium and you cannot take advantage of the voltage potential. Maybe you can tell us how lightning strikes play a part in that.
Well, it's not the... go back one.
Sure. Lightning strikes, after that spark happens, now the atmosphere directly above that ground theoretically should be the same voltage potential now. So it's neutral.
Right. But what we're looking to extract is the RF that's produced.
Okay.
And that's probably right about at the zero node when it's released. And what many may be referring to as 0-point energy. The energy is released at that zero node point in the form of RF. Many wavelengths.
Are these two separate processes, what you've got going on the table and what you're describing?
Yes. Actually today I described 3 different energy sources. One is the getting energy out of the atmosphere to the ground, through getting the energy that's released by lightning. And the lightning is a result of the cosmic particles coming from the sun that's charging the ionosphere. And as the clouds move across the earth, the energy is induced in them. They build up enough charge and they discharge and release this energy. Now all we have to do is capture it. But the source of energy still originates from the sun. Just the way we're capturing it differently. Okay, I have to end here. I can talk to you after we get done here. I'm out of time. Thank you.